Today's lesson is on energy. We use the capital letter E to represent most energy variables, and it is defined as the ability to do work. It is measured in joules, which is represented by a capital J when you use it as a unit. The first type of energy we're going to talk about is kinetic energy, which we use E sub K, and sometimes we'll short form as KE instead of writing out kinetic energy. And it is defined as the energy of a moving object. So it's the energy that is basically possessed or owned by an object that is moving. I've drawn a quick little free body diagram. When we calculated work in the previous lesson, we looked at work done by an applied force and work done by the force of friction. So we want to consider the total work or the net work. So we know that the net force is the sum of forces, so it makes sense that net work, we're going to add our forces, or add our works here. And we know that friction is the opposite direction of the applied force, so we end up with negative work there. So that's why I've shown the cosine of 180 degrees, just to remind us that we end up with negative. So when we pull out the delta D, because delta D appears in both parts, we end up with FA minus FF. And FA minus FF is just the net force. So net force times the displacement is the net work. And this will be true for all situations everywhere. But F net is also mass times acceleration. And from one of our kinematic equations, we also know that acceleration times displacement is the difference of squares of the velocities over 2. So I can substitute that in. And then I basically end up with two statements. Mass times v2 squared over 2. And mass times v1 squared over 2. And it turns out that these statements are kinetic energy. So what we have here is the final kinetic energy minus the end kinetic energy, and let's just for simplicity's sake say we're in a situation where that initial velocity is 0. So this goes to 0, and what we're left with is mass times v2 squared over 2. So kinetic energy is 1/2 mv squared. We will often use what is called the work energy principle to solve problems. And this principle is the amount of work done on an object is the same as the change in its kinetic energy. And that is pretty evident from the previous slide, where we ended up with 1/2 mv2 squared minus 1/2 mv1 squared. So the amount of work on an object is the same as the change in its kinetic energy, or the difference between its start and end kinetic energy. So here we have an example. A 50 kilogram ice hockey player going 4.0 meters per second slows down and stops. What is the net force acting on the skater if she travels 1.2 meters? Now we can technically solve this problem using our forces equations that we did in the last unit, but I'm going to show you how to solve this with energy as well. So I've listed out my givens and requireds, and I can draw a diagram to show what's happening as well, but I don't really know any details of the forces, so it would be harder to solve this using forces, but it's still doable because we have enough kinematic info to find acceleration, and then to use acceleration to find F net. And we're kind of doing the similar thing when we use energy, but we're going to use the work energy principle. So we know that work is the change in kinetic energy. And we also know that work is F net times delta D, because it's basically net work that we're looking at here, and that here is 1/2 mv2 squared minus half mv1 squared. And we know that v2 is 0, so this part goes to 0. And we're looking for net force, so now we just have to divide by delta D. So we get negative mv1 squared over 2 times delta D. Substitute in our numbers. And I just have to pause for a sec because I forgot to bring a calculator with me. So we end up with negative 333 newtons. So therefore, the net force acting on the player is 333 newtons backward. So our last type of energy is gravitational potential energy, which we will sometimes shorten to GPE, and the symbol is E sub G. And it is the energy of an object because of its height above Earth's surface, but we can calculate it relative to any reference level, not just Earth's surface. So I want to show that we can show that GPE is related to the concept of work, because you already know that work is related to kinetic energy. So we're going to consider here, so we know that GPE has to do with height above something, and if you think about it, the only reason that something would have energy because of its height must be related to gravity. And it turns out that E sub G is mass times gravity times height. So if we want to show that this has anything to do with work, we need to show that it is force and displacement. Well, force, this is essentially the force of gravity, mass times G, and height is our replacement for the up and down displacement. So you can see that is definitely very much related to work. The key here is that this is your equation for gravitational potential energy. So if it's related to work, it must also have some connection to kinetic energy, which makes sense because if we drop an object, it starts with 0 kinetic energy and a bunch of GPE, and then we let it go as it's falling, it's decreasing in GPE and increasing in kinetic energy. I just want to quickly show you that GPE can be negative or 0, depending on our reference level we choose. So let's say we have a table, and we're thinking about an object that's above a table. So here's the object. So it has a certain height. And if we use the table as a reference level, then it has this height. And let's say the table here is another meter off the ground. So this object at this point, we could use mgh and just sub in this particular h here. We just sub in this h. But we could also do the object relative to the ground. So then we'd use h plus 1. But we could also have an object that's below the surface of the table. And if we're using this as our reference level, now we're having a negative height. So let's say here that we've got negative 0.5 meters. So it's kind of halfway below. So that means when we do our GPE, we're going to end up with a negative value because you're going to plug in a negative h, and then your m and g are positive. So we'll end up with a negative EG. So Eg is positive when above the reference level, and negative when below the reference level. And the last kind of little definition you need is mechanical energy, which we often write as E sub T, known as another way of as total energy. So total energy or total mechanical energy is the sum of kinetic and gravitational potential energy. So sometimes we'll be considering adding the kinetic and GPE of an object together. And when we do that, we call it mechanical energy or total mechanical energy.